All right, let's talk about running a factory. Sounds pretty simple, right? You make a thing, you move it to the next step, you repeat the process. But what if I told you that when you're dealing with complex systems like a factory, your gut instinct, your intuition, is almost always wrong? Let's step onto the factory floor and see just how wrong it can be. So here's our puzzle. A simple 12-workstation factory. Products just flow from station A to B to C, all the way down the line to L, and then they're out the door. It looks incredibly straightforward, doesn't it? A nice, neat, linear process. But this simple-looking system is hiding a massive, massive problem. And that problem? It all comes down to this one number. This is the source of all the headaches. 90.42 days. Yeah, that's the cycle time. The total time it takes for one single item to get from the very first workstation all the way to the last. We're talking more than 3 months in a factory that's supposed to be efficient. I mean, something is seriously, seriously broken here. Okay, so now you're the manager. They just handed you a $13 million budget and said, fix it. So what do you do, right? Do you, I don't know, buy a bunch of new machines? Yell at the slowest workers to speed up? Where do you even begin? And this, right here, is where your gut is probably going to lead you completely astray. So instead of just guessing, let's be smart about this. We're going to play detective. We're going to hunt down the real problem, the bottleneck. And all the clues we need, they're right there in the data. Okay, don't get overwhelmed by all these numbers. You don't have to read it. Just think of this as our crime scene. This spreadsheet has all the performance data for the entire factory. The answer to that ridiculous 90-day problem, it isn't walking around on the factory floor. Nope, it's buried right here somewhere in these numbers. We just have to know what to look for. And the crazy thing is, the clues are hidden in plain sight. See, we're not looking for the slowest workstation. That's what your gut tells you to do. We're also not looking for the one with the fewest machines. We're looking for the one that's under the most stress, the one that's running completely flat out, full speed, and still can't keep up. In manufacturing lingo, we call that the station with the highest utilization. And bingo! Just like that, the data points right to our culprits. Take a look at the utilization rates for workstations D, H, and K. They're all running at 98% capacity. I mean, they are completely redlining. These aren't just kind of slow. These are the bottlenecks. They're the ones choking the life out of the entire system. This whole idea brings us to this really powerful management principle. It's called the theory of constraints, or TOC for short. And the core idea is actually super simple. Any complex system is limited by its single weakest link, its constraint. So, and this is the critical part, if you want to improve the whole system, you must ignore everything else and pour all your energy into fixing that one single constraint. So that's exactly what we did. We took that $13 million and we invested it only in workstations D, H, and K. We didn't touch a single other part of the factory. And the result? Well, the cycle time absolutely plummeted. It went from over 90 days all the way down to just 21.84 days. I mean, just look at that drop. That's a nearly 76% reduction in the time it takes to make something. That is the power of using data instead of your gut. We found the real constraints, we fixed them, and we got this massive improvement. It's a huge win. But the story is not over, not by a long shot. In fact, things are about to get really weird. Which brings us to this really fascinating and kind of dangerous idea I like to call the improvement trap. It's this weird situation where your logical, well-intentioned desire to make things better can actually make everything a whole lot worse. I mean, think about it. It seems logical, doesn't it? We just saw improving the bottlenecks had this massive positive effect, so it stands to reason that improving any workstation, even just a little bit, has to be a good thing, right? I mean, it can't possibly hurt. Can it? Well, you might want to brace yourselves for this one. This graph shows what happens when we totally ignore the bottlenecks, and instead we pump a bunch of resources into workstation A, which is not a bottleneck. And look at this. At first, the cycle time drops just a tiny bit, but then it starts to climb and climb. By making workstation A faster, we are making the entire factory slower. How on earth is that possible? This is honestly one of the most important and totally counterintuitive lessons you can learn about how systems work. Improving a part that isn't the problem literally makes the whole problem worse. But why? Okay, imagine this. Workstation A is now a fire hose. It's just blasting out parts at an incredible speed. But the very next step in the line, our bottleneck, is still just a tiny garden hose. So what happens? All you're doing is creating a massive flood of inventory. It just piles up, it drowns a factory floor, it causes chaos, and it slows everything down. You've optimized one little piece, but you've completely wrecked the entire system. Okay, so this all leads us to our final showdown. We're about to challenge one of the absolute giants of manufacturing philosophy. We're talking about the balanced line myth. You know, for decades, one of the core ideas in manufacturing, especially in lean manufacturing, has been this idea of the balanced line. And the quote here really says it all. The goal, the ideal, is to have every single workstation processing jobs at the exact same rate, all perfectly in sync with what the customer wants. I mean, it sounds beautiful, right? It sounds elegant, it sounds super efficient, but is it actually true? So to put this to the test, we're going to use a much simpler model, just 5 workstations, and it's designed specifically to test this one idea. Can a perfectly balanced factory really outperform one that isn't? And the results are just stunning. Seriously. On the left, you see the balanced line strategy. Every workstation is running at the same target speed. The cycle time? Over 100 hours. Then on the right, you have the unbalanced line strategy. Here, we just let every workstation run as fast as it possibly can. The cycle time? Just over 5 hours. It's not even a contest. The so-called unbalanced line is nearly 20 times faster. The myth? Completely busted. So what's the big takeaway from all this? What's the moral of the story? It's really simple, but it's also profound. When you're dealing with a complex system, you have to trust the science, not your gut. All right, let's just quickly recap what we've learned here. Number 1, your factory or, hey, your project, your team, whatever, it's only as fast as its slowest part. That's it. Number 2, improving something that isn't the bottleneck isn't just a waste of time, it can actually be harmful. Number 3, that really nice, elegant idea of a perfectly balanced line, it's usually a trap that just leads to massive inefficiency. And finally, the most important one of all, in any complex system, data is always going to beat your intuition. And I really want to leave you with this powerful quote that sums it all up. In short, factories are complex systems, and no matter how intelligent and experienced you might be, you can rest assured that your intuition is almost always wrong. Which, leads me to one last thought. We've been talking about a factory this whole time, but this lesson applies to, well, everything. So the question I want to leave you with is this. Where in your work, or maybe even in your life, is your gut instinct about what to fix the very thing that's actually holding you back?